In this video, you'll be introduced to the concepts related to oscillations. Most of the time, we'll be talking about simple harmonic motion. Any motion that repeats itself is called periodic motion or harmonic motion, but simple harmonic motion is special. We'll learn more about what makes it special in a moment. For periodic motion, we have an expression for the displacement of the particle. As you can see here, that expression is related to the cosine of a function. X of t, the position as a function of time, is given by x sub m times the cosine of omega t plus phi. This is an expression that you should memorize. It is not on your equation packet, and you will need to know it. This is one of the few equations I will tell you to memorize in this chapter. Let's look more at that equation. The first portion, x of t, that gives us the displacement at a specific time. X of m is the amplitude, the furthest away our object gets from equilibrium. Some textbooks also use a capital A in place of this x sub m. You can memorize it either as a cosine of omega t plus phi or x of m cosine of omega t plus phi. Either is fine. You also see that there's an angular frequency here. Angular frequency is very similar to angular speed in that it's the number of radians per second. It's related to the plain old frequency, which we learned about last year. Frequency is represented by the script letter F and has a unit of hertz, Hz. That tells us how many times it goes through a cycle in 1 second. The period does not appear in this equation, but it is related to some of the quantities here. It's represented by the capital letter T, and it is measured in seconds. The relationship between period and frequency is that the period equals 1 over the frequency. The angular frequency, omega, is also related to the linear frequency, in that it is 2 pi times the linear frequency. The other variable that we have in this equation is called the phase constant, sometimes called the phase angle. This tells us about the starting conditions. If you look at a position versus time graph, and it looks just like a normal cosine graph, then your phase angle is 0. Most of the time, that doesn't happen. Often we'll start time t equals 0 when it's not at the maximum displacement or amplitude. In this case, we will have a value for phi, and we will learn how to calculate that value. Now that we understand the displacement equation, or really the position equation for simple harmonic motion, we're now going to look at velocity and acceleration equations in simple harmonic motion. Again, this equation for x of t is for objects that are in simple harmonic motion only. So when we know something's displacement, how do we find its velocity? Hopefully you answered by saying that to find the velocity, we take the derivative of the displacement. V of t equals dx dt. So we're going to do that right now. We're going to take the derivative of this function. X of m is a constant. So that constant times the derivative of the cosine. Derivative of cosine we know is negative sine. Because there is a t in our argument, we must use the chain rule. So since we've already taken the derivative of that cosine, we then take the derivative of what's in parentheses, and we get that the derivative is omega. Rewriting that gives us the function v of t equals negative omega times x of m times the sine of omega t plus phi. So the velocity function normally looks like a negative sine function. So it starts all the way at the bottom valley. Okay, well, what about finding the acceleration? If we know velocity, then we can say that the acceleration is equal to dv dt. But velocity is the derivative of displacement. So that's d dt of dx dt. It's the derivative of a derivative. We can write that, express that as d squared x over dt squared. Let's take the derivative of this velocity function. We know negative omega and xm are constants. The derivative of sine is cosine. And then we have to take the derivative of this expression in parentheses, which again is just omega. Simplifying that expression, we get that the acceleration is negative omega squared xm times the cosine of omega t plus phi. Now you'll notice that xm times cosine of omega t plus phi is just x of t. So the acceleration is negative omega squared times x of t. As it says here, that is characteristic of simple harmonic motion. The acceleration is proportional to the displacement, but opposite in sign, and the two are related by the square of the angular frequency. This diagram just gives you an idea of what these three functions look like when the phase constant is 0. They may not look perfectly like this for many of the problems that we see, but this is what they look like when the phase constant is 0. We've already dealt with displacement, velocity, and acceleration for simple harmonic motion. The natural next step is force. If we know in simple harmonic motion that acceleration is proportional to the displacement and opposite in sign, what can we say about the force? Well, we can say the same thing because we know F equals ma. So then F is also proportional to the displacement and opposite in sign. The technical definition of simple harmonic motion is that it is the motion of a particle that is subject to a force, and the force is proportional to the displacement of the particle but opposite in sign. If it's a linear simple harmonic oscillator, then the force is proportional only to x, not to x squared or x cubed. Most of what we deal with are examples of linear simple harmonic oscillators. When this is the case, the angular frequency is equal to k over m. Most of the time we'll be dealing with springs in this case. So k is the spring constant, m is the mass attached to the spring. This does work for other objects as well. K will just be some other constant. The last concept about periodic motion, about oscillations to talk about, is energy. Here I'm talking specifically in context of the spring. We have a spring that is displaced, and we want to know what happens to the energy of that object. Well, when you first displace that spring, it has elastic potential energy. We know that equation is 1/2 kx squared. For an oscillator, we can write an expression that tells us how much elastic potential energy it has at any point in its motion. that equation just plugs in the value for x of t. So xm cosine of omega t plus phi. Simplifying this, I get 1/2 k xm squared times the cosine squared of omega t plus phi. We know that this is at a maximum when the cosine of the angle or cosine of the expression is 1, which happens to be at the amplitude. As we release our object, some of this elastic potential energy gets transformed into kinetic energy. We can do the same thing with kinetic energy, plugging in our expression for velocity. In that case, it's negative omega xm sine of omega t plus phi squared. Squaring that expression yields 1/2 m omega squared xm squared sine squared of omega t plus phi. The maximum kinetic energy occurs when the sine is equal to 1. Well, we know that that happens when this expression equals 90 degrees, or pi over 2 radians. That happens at a different point than where we have a maximum elastic potential energy. Specifically, that happens at the point where there is no elastic potential energy, which is at equilibrium. At that time, that maximum kinetic energy is equal to 1/2 m omega squared xm squared, xm being the amplitude. We can do conservation of energy just as we have in the past. Sometimes it is useful to use these larger expressions. Again, it's unnecessary to memorize any of these because taking the derivative of that displacement function is rather simple. Just make sure you have the displacement function memorized. Now, if you haven't done so already, in the notes packet, go through and answer these understanding check questions. We'll check them in class.